Hi, I am Arata Jingu and a second-year PhD student at Arata University. I'm going to talk about our work shaping compliance, inducing haptic illusion of compliance in different shapes with electrotactile grains. This work was done in collaboration with my co-authors Nihar Sabnis, Paul Strohmeier, and Jürgen Steimle. So, what is compliance? Compliance is a material property that indicates the degree of displacement and the applied force. It has a pivotal role in determining material perception of an object, such as elasticity, softness, or depth of displacement. Due to its importance, researchers have proposed methods of virtually creating compliance. As compliance is expressed as a relation between force and displacement, the basic approach is altering perceived haptic sensation when the user presses the object, such as adding kinesthetic cues, vibrotactile cues, skin stretching cues, and restriction of the finger deformation. Among them, the grain-based vibrotactile compliance illusion is widely used and deeply related to my approach. I explain its principle using this example device that provides virtual compliance when the fingers are actually pushing a hard box. This device comprises a force sensor and a vibrotactile actuator. First, the available range of the force sensor is divided into discrete bins. When the force value changes and moves into a different bin, the device generates a short mechanical vibration, which is called a vibrotactile grain. Surprisingly, this resulting vibrotactile pattern nicely produces a haptic sensation of pressing a compliant surface. This illusion is popular for compliance rendering because it can express various compliant materials with adjustable parameters and requires only off-the-shelf components. Despite its high potential, vibrotactile simulation has one major limitation in rendering compliance. The spatial resolution is low since the vibration propagates through the skin. Therefore, vibrotactile approaches have always rendered compliance for the entire finger rather than providing localized cues. This lowers the expressiveness of compliance rendering, considering real-world compliant objects have various sizes and shapes, and the user touches them with different areas of the finger. This limitation applies not only to vibrotactile compliance illusion, but also to all the other compliance rendering methods. To tackle these issues, we propose a novel grain-based electrotactile compliance illusion. This illusion renders compliance in different shapes with a skin-conformal interface, comprising printed circuits and a force sensor. Inspired by the grain-based vibrotactile illusion, our approach creates a sensation of a compliant surface by generating a set of electrical pulses in response to the force changes. We call this single set of pulses an electrotactile grain. I explain electrotactile stimulation briefly. It can elicit localized tactile stimuli comparable to the skin's tactile spatial resolution by directly applying the electrical current to the skin via electrodes. We can easily make a thin, flexible electrotactile interface with conductive inkjet printing or flexible PCB. We can also render two-dimensional shape and spatial temporal feedback by switching multiple electrodes at high speed. Using this localized sensation of electrotactile stimuli, our illusion renders compliance in different shapes, such as a large square, horizontal line, vertical line, or small square. Electrotactile compliance illusion has various adjustable parameters affecting the sensation. Especially these two parameters, number of grains and shape, are most important in this initial exploration. According to previous vibrotactile compliance illusion works, the number of grains strongly affects the magnitude and quality of perceived compliance. More grains usually create the perception of higher compliance because they produce compliance cues more frequently. Shape is a unique parameter to the electrotactile illusion. We created shapes made of 4 or more active electrodes as the pilot study's participants did not feel enough compliance magnitude with fewer electrodes. Our first user study was done to investigate the effect of these parameters on compliance magnitude. The task had 2 conditions of 3 grain levels, 9, 19, 39 grains, and 4 shapes, large square, horizontal line, vertical line, small square. Participants pressed a hard desk surface under each condition and rated the relative compliance magnitude compared to when just pressing without stimuli. They were instructed to map the rating score only to perceived compliance, not the electrical stimulation intensity or the size of the stimulated area. The result confirmed that the proposed illusion can induce virtual compliance compared to the reference condition of no stimulation, and perceived compliance magnitude was intensified with an increasing number of grains or electrodes used. As for the grains, a significant difference was found between all grain levels. Here, 0 means no stimulation. Similarly, as for the number of active electrodes in each shape, a significant difference was found between all electrode number conditions. Here, 0 means no stimulation, 4 means small square, 6 means vertical or horizontal lines, 9 means large square. This result indicates our approach can adjust the magnitude of perceived compliance with at least 4 grain levels and at least 4 electrode number conditions. Our second study aimed to verify that the proposed approach can make the user perceive virtual compliance with specific shapes. We chose 5 shape conditions: large square, horizontal line, vertical line, small square, and triangle. Participants experienced each condition and were asked to draw the contours of the areas they felt compliance, not just electrical stimulation. These heat maps visualize the overlaid contours for each shape condition. Our participants were able to draw quite accurate contours despite the demanding nature of this task, such as the small electrode spacing and the sensation variability between persons. This indicates the proposed illusion can render compliance with specific shapes. We also collected qualitative feedback after these studies. First, as for the induced sensation in a study, participants described similar expressions to the vibrotactile compliance illusion, such as elastic, squeezy, compress further, and feel as if the surface displaces when pressing hard. Next, we asked participants which real-world object was reminded by the induced sensation. They answered some compliant objects such as sponge, phone, pillow, grass. As one interesting aspect, some participants mentioned they felt compliance with a large surface texture. It is attributed to localized electrotactile stimuli and quite different from the vibrotactile illusion that renders compliance with a smooth surface texture. In future work, the electrotactile illusion might be able to render compliance with various surface textures. Based on these results, I demonstrate 3 applications that show how our electrotactile compliance illusion augments various interfaces, such as touch screens, physical objects, and virtual reality. Our approach renders compliance when the user reads a picture book and touches an illustration, such as a large area of soft grass, a squishy horizontally shaped dog nose, and an unripe and hard small vegetable. Our approach renders compliance when the user touches an item of an online shopping website on a touch screen, such as a large fluffy cushion, an elastic vertical sleeve of a jacket, and a horizontal stick strap. Finally, our approach can be useful in a video medical training for medical staff to find veins or to assess the skin surface conditions of a patient through palpation. When the user touches a physical hand model, our device presents a sensation of soft skin underneath the whole finger pad, a thin and stiffer vein. In summary, we propose a grain-based electrotactile compliance illusion that creates virtual compliance in different shapes. It is not restricted to the wearable device form factor shown in this work. We are excited for its various forms in future, such as grounded electrotactile displays, more high-resolution devices, and ultra-thin membranes.